Okay guys, so I'll start with feedback. So to know what feedback is, if we take a diagram like this, a system like this, so to this system we give an input of x is from a source, and this this is an amplifier, so this amplifier gives the output x naught. So what we do is we sample this output and take a portion of this multiplied by beta, which we call x8, and this is the feedback. So we can add this, either add this feedback to this input or subtract this from that. So that result will be the input to the amplifier. So this is a general feedback structure. So depending on whether we add this or subtract this, there are two types of feedback. So if we add this, it will be a positive feedback, and if we subtract this, it will be a negative feedback. So in a positive feedback system, let's suppose that the output increases. So when the output increases, you know that xf or feedback also increases. So since we are adding this to the input, it will increase xi and further increase the output, right? So that is how a positive feedback system works. So positive feedback systems are usually used to make oscillators, right? And if we take a negative feedback system, let's say that the output has increased, so you know that the feedback also increases. So then in that case we subtract this feedback from the input, so therefore xi will reduce, and this will cause the output to go down or reduce. And negative feedbacks are usually used in amplifiers. Okay, so there are two things that we need to know. This A, so this A is called the open loop gain of this amplifier, right? So this is the open loop gain, and this beta is called the feedback factor. So using these two, let's try to find the overall gain of this system, that is what we call the closed loop gain, which is denoted by AF, right? So to start the calculation, so we can, at this point we can write that xi is equal, so I'm going to consider a negative feedback system. So in a negative feedback system, xi will be equal to xs minus xf. So it is at this point, right? And considering the amplifier, I can write that x naught, or the output, is equal to a times x input, considering this amplifier. And also considering this feedback, I can write that xf feedback is equal to beta times the output. So the closed loop gain is actually x out divided by xs, that is the output of the system, divided by the input of the system. So we need to find the relationship between these two. So I'm going to use this equation. So using this equation, I can replace xi with, using this equation, with x out divided by a, and we need xs for the final equation, so I'm going to keep xs here, and xf can be replaced by beta x naught. So if I take x naught to one side and take it as a factor, we can write x naught times 1 over a plus beta is equal to xs. So let me write it here. So if I add this together and simplify this, I can write x naught is equal to a over 1 plus a beta times xs. So using this, I can write this closed loop gain AF is given as open loop gain A divided by A plus A beta. So you can see that the closed loop gain is reduced than the open loop gain. Also, there is a small assumption that we can make in some systems. If this A beta this product, if this is larger than 1, considerably larger than 1, we can further simplify it. So if I divide both the numerator and denominator by a beta, I can write this as 1 over beta divided by 1 over a beta plus 1. So if this is far greater than 1, that is 1, then we can neglect this 1 over a beta. So this will make a or the closed loop gain approximately equal to 1 over beta. A beta product is far greater than 1. Okay, so next let's discuss about these features or characteristics of this negative feedback. So consider this, there are 4 properties of negative feedback. So first one is the gain desensitivity. So gain desensitivity means that if there is a large change in the open loop gain A in a negative feedback system, it will only cause a small change in the closed loop gain, right? So this is what gain desensitivity is. So let's see how we can show that, right? So we know from the previous part that the closed loop gain of a negative feedback system is given by this equation, right? So what I'm going to do is I'm going to take the derivative of this with respect to a. So I'll get dA over dAf over dA. So if I do this, I'll get this denumerator times the derivative of the numerator minus numerator times the derivative of this, that is beta, divided by the complete square of the denumerator. So simplifying this will give me 1 over 1 plus a beta whole thing squared. So if I take this dA to this side, I can write dAf is equal to 1 over 1 plus a beta squared times dA. Now what I'm going to do is I'm going to divide both sides from a. So let's see what happens. So we know what AF is. So to this side I'm going to substitute this. So then I'll get that DAF or AF is equal to 1 over 1 plus A beta square times 1 over sigma 1 dA over A divided by 1 plus A beta. So if I simplify this, what I get is DAF or AF. So this is like a fractional change of AF, or the percentage change in AF. If I multiply this by 100, is equal to 1 over 1 plus A beta times dA over A. So dA over A means the percentage change in A, and dAF over AF is the percentage change in A on the closed loop gain. So this means that a larger percentage of change in the closed open loop gain will be a smaller percentage of change in the closed loop gain. So this open loop gain will be divided by this factor of 1 plus A beta. So this is what the gain desensitivity is, and it's an important property of negative feedback. Okay, so then the second property of negative feedback is bandwidth extension. So this is also very important, because that is, if we give a negative feedback to an amplifier, it will increase the range of frequencies that it can amplify without distorting the signal. So let's see how we can show this. So I'm going to use two parts. So the first part is, let's consider the higher frequency response of an amplifier. So I'm going to model it using this equation. So it will be A equal to AM divided by 1 plus S or omega H. So this is the transfer function in Laplace domain. So this omega H is the 3 decibel upper cutoff frequency, right? So if we draw a graph, it will be like this. So this is where omega H is the upper cutoff frequency, right? So this AM is the mid band gain. So it's another thing, right? So let's see how this will change when we add a negative feedback. So if we give a negative feedback, we know that what happened is our new gain for the closed loop gain will be A over 1 plus A beta. So if I substitute A here, what I get is AM divided by 1 plus S or omega H divided by 1 plus AM beta divided by 1 plus S or omega H. So if I take a common denominator here, so I'm going to have something like this. So this common denominator will cancel off. This will be AM over 1 plus, I'm going to rearrange this a little bit, like 1 plus am beta plus s over omega h. So then what I'm going to do is I'm going to divide both the numerator and the denominator by this factor. So now I will get af is equal to am over 1 plus am beta divided by 1 plus s over omega h times 1 plus am beta. So you can see that in this new gain transfer function there are two changes. First of all, this mid-band gain, you can see that it is reduced by a factor of 1 plus am beta than the previous one. And also here, this part, we can consider this as the upper cutoff frequency of 3 decibel. So you can see that it is multiplied by this factor, so that means this upper cutoff frequency is increased. So if we redraw this graph, now it will be something like this. So our new cutoff frequency is somewhere around here, and mid-band gain is reduced. So you can see that negative feedback increased the bandwidth of this. Okay, so the next one, so that was the high frequency response. So let's just consider the low frequency response. So we can also model the low frequency response using a single pole, like A equal to AM, which is the mid-band gain, divided by 1 plus S omega L, where omega L is the lower cutoff frequency, lower 3 decibel cutoff frequency. So if I draw a graph, plot, it will be like this. So this will be omega L, right? So again, we can use that formula, A equal to A over 1 plus A beta, and substitute A and see what happens when we give this feedback. So here it will be the same procedure as before. So you have to just substitute this one for A. So then it will be like this, right? So if you simplify this, write the final answer, so it's like very much like the previous one. So if we simplify this, what we get is this AM divided by 1 plus AM beta. So again, you can see that the mid-band gain is reduced by this factor, plus divided by 1 plus S times omega L divided by 1 plus AM beta. So this is the new lower cutoff frequency. So you can see that it is divided by this factor, so that means the new lower cutoff frequency is reduced. So it is somewhere around here, right? So that means again there is an extension in this bandwidth. So if we consider a complete band pass, complete band, and consider the body plots. So if we take the open loop gain, the body plot will look something like this, right? So suppose that this, if I mark this, so these are the 3 decibel cutoff frequencies, and if we consider the closed loop gain, it will be something like this. So now you can clearly see that this 3 decibel gain band is increased by reducing this lower cutoff and increasing the upper cutoff. So this difference is, we can write log 1 plus a and beta, because this is actually in the log scale in frequency, right? So this is in the log scale of frequency, and this change in this gain here, the reduction in midband gain, it is 20 log 1 plus am times beta, right? So this is how the body plots look like. So you can see that there's a clear increase in bandwidth. So that is the second property, bandwidth extension. Okay, so the third property of the negative feedback systems is noise or interference reduction. So you know that noise or interference is a critical thing when it comes to amplifiers and communication and everything. So let's suppose that there is an amplifier here with a gain of A1. So let's say that it is affected by a noise Vn here at its input, right? So this will cause some problems in the output, as you know, right? So let's try to find the signal to interference ratio at the output. So here in this case we can write the output as A1 times Vs plus V noise. So the output has two parts then, A1 times Vs, which is the signal part, and A1 times Vn, which is the noise part. So dividing the signal part and noise from the noise interference part, or the noise part, we can get that the signal to interference ratio here is Vs over Vn, right? So which is the same as the signal to noise ratio in the input, right? So let's see how we can reduce this using a feedback system. Let's see how this noise interference reduction is done. So in this case, what there is a certain condition. So that condition is that we should be able to add a clean amplifier in front of this amplifier. So a clean amplifier is an amplifier which has no effects of noise at the input, right? So if we can add an amplifier like this, we can reduce this noise or interference, right? So if you see this diagram, it may look a little bit complex, but I'll explain it to you. So if we have this source here, Vs, and let's say I'm going to mark this voltage as the input voltage Vi, and this is what we do is we have given the feedback. So we have taken V out here, so this is V out, and this voltage out here is like this, beta times V out using polarity like this. So if we write the Kirchhoff's voltage law to this loop, we can write that Vs is equal to Vi plus beta times V out, right, using this loop. So in that case we can write the input voltage Vi can be written as Vs minus beta times V out, right? And further, if I take this as E1, right, so E1, which is input, so we can write that V out is actually equal to A1 times V1 plus Vn, and also V1 is this amplified version of Vi, so V1 will be A2 times Vi, or if I substitute this here, I can write V1 as A2 times Vs minus beta V out, right? So if we do the small simplification here, so I can write V out as A1 times V1 here will be replaced by this, it is A2 times Vs minus beta V naught, Vs here, plus Vn. So from this I get V out equal to A1 A2 times Vs, so there will be A1 A2 beta times V out here, so I can take this it to this side, so I will have 1 plus A1 A2 beta over this side, and plus A1 Vn, right? So within this I can write that V out is equal to A1 A2 divided by 1 plus A1 A2 beta times Vs plus A1 or 1 plus A1 A2 beta times Vn. So now we have a signal part and a noise part. So if we calculate the signal to interference ratio now at the output, this part divided by this part, so you can see that this A1 over this is common to both, so it will be Vs over Vn times A2. So without the feedback, what we got was this Vs over Vn. Now we have Vs over Vn times A2, so that means that signal to interference ratio has been improved by this clean amplifier, right? So that's it. So in that case we can reduce this noise to interference, so noise or interference. And also another important thing is that if we choose this feedback factor beta large enough, we can maintain a very similar gain as before, like there was no feedback, right? So we can keep the gain while reducing the noise or interference. Okay, so the fourth property of the negative feedback systems is this reduction in nonlinear distortion. So if we take transfer characteristics of an amplifier, so you can see that is input voltage, output voltage versus input voltage. So this graph is a piecewise function, right? Piecewise linear. So in that case, so let's say that gain here will be 1000, and let's say again in this part is 100, right? And so is this. So actually this piecewise linearity causes a lot of distortion, so it will cause a nonlinear. So this is a nonlinear characteristic, so it generates a large amount of nonlinear distortion to the signal, right? So we can reduce this by using feedback. So let's see how we can do that. So suppose that we add a negative feedback to the system with the feedback factor of 0.01, right? So let's calculate gain at each of these intervals using this closed loop gain function A equal to A over 1 plus A beta. So if we take the portion where A or the open loop gain is 1000, we can substitute that, and you see that this is 1000 divided by 1 plus 0.01 times 1000 is 10, so that is 1000 divided by 11, it is 90.9, right? And similarly we can calculate the value when A is 100. So in that case you know that 100 divided by 1 plus 1, so answer will be 50. So in this range, these two ranges, the new gain will be 50, and in this range it will be 90.9. So if we draw this, you will see that there will be a significant change in the gain characteristic, right? So it will be something like this. So this gain is 50 here, this is also 50, and gain in this part is 90.9. So you can see that non-linearity has been reduced by this introduction of the feedback. So we see that by introducing negative feedback we can reduce non-linear distortions from an amplifier. So that's all for the feedback and the characteristics of negative feedback.